So hello everyone and welcome to Pepperwood's webinar series. My name is Stephanie Antonoro and I'm Pepperwood's communications coordinator. I'll be facilitating today's webinar. Pepperwood is a 3,200 acre preserve located in the Mayacamas Mountains of Northern California within the ancestral homeland of the Wapo people. Pepperwood also serves as a Sentinel site or field station, which you are going to learn a lot more about today. There are more than 700 individual data streams continuously collecting data on our soils, water, weather, climate, and biodiversity. We've been gathering data in this capacity for over 12 years now, and the impact of that work is something our presenter is about to talk about in great detail. And with that, I'd like to present today's speaker, Ryan Ferrell, as Pepperwood's Sentinel Site Manager. He was born and raised in Santa Rosa, and he is an avid outdoorsman. He spent much of his free time on the rivers, wetlands, farmlands, and coastal mountain ranges of the Bay Area and Greater California. He attended UC Davis, where he earned both his undergraduate degree and a master's of science in soils and biogeochemistry. His thesis work focused on mapping and modeling regolith thickness for the western slope of the Sierra Nevadas of California and linking that thickness to water storage and its effect on forest susceptibility to drought-induced mortality. As Pepperwood Sentinel Site Manager, Ryan is in charge of Pepperwood's rapidly expanding wireless meteorological and soil sensor network, and he's in charge of data management and acquisition from these systems. He's dedicated his career to science, but it's more than that for him, as you'll undoubtedly perceive in the following presentation. He's passionate, knowledgeable, and deeply invested in conservation science. I think it is safe to say that science is more than a career for Ryan, it is his life. And with that, Ryan, please take it away.
Awesome. Thank you, Steph. So thank you, everybody, for being here. It's sort of a first for me talking to the screen, so I hope you all are still there and tracking. Anyways, yeah, it is my goal here in the next, well, I'm going to try to keep it under 40 minutes. I think I can, to give you a high-level overview of what is a Sentinel site, what we do as a Sentinel site, and then make the most important leap. How does what we do up here affect the natural world, and how does that affect you as part of the natural world? And to kind of dispel that idea that, there's the natural world over here and us and humanity is over here. We really are tied into the natural world. We enjoy so many of those resources that we get from the ecosystem, these ecosystem services. And so that'll be one of the themes here. And ultimately, providing the link from the abiotic, kind of the non-living world, our drivers of climate change, to the biotic world, which includes us. So let's go ahead and move forward. It's already not moving. There we go. All right. So first and foremost, the Sentinel site. What is a Sentinel site? And this is just a very high level description here. I immediately go to the word Sentinel, and I think of a sentry. I think of the general orders of a sentry if you have a military background. The second one, keeping always on the alert and observing everything that takes place within sight or hearing. Or in other words, I mean, take that to mean just monitoring and observing everything. And the sentries across Pepperwood, across our 3,200 acre preserve, are all these installations and monitoring plots that we have across the preserve. And all those sentries make up the Sentinel site that is Pepperwood. And, that's what we do. We stand watch in perpetuity with all those data streams while we're at home behind our four walls, asleep in our beds under climate control. These sensors and data streams run continuously and capture all those fine resolution things at 15 minutes or whatever time interval we choose. And then we do an awful lot of investigations downfield and monitoring downfield in these forest plots. And that's where our human resources, our researchers, interns are down there taking a lot of these measurements. And I have to point out here, and I will mention this a few times, Pepperwood and an individual station is just that. It's one place in this extremely biodiverse landscape that is, well, Pepperwood or Sonoma County or California or the world in its entirety. And so you have to be careful about, when we look at certain data streams here, what does that really represent? And where can we extend what we know here at Pepperwood? Where can we extrapolate and extend and say, hey, what's happening here at Pepperwood is likely to happen over there? And so that's a recurring theme. And in looking at trying to perform rigorous, defendable science, that's something that we always have to keep in mind. The image here on the right-hand side of your screen, this is Pepperwood's Hill 1524. And something that makes Sentinel sites so fantastic is they serve as these regional hubs for all kinds of research. And a huge shout out, Pepperwood has a relatively small team, but so many different players and scientists and researchers come to Pepperwood to utilize our, our network and our framework of data, and they add to it and they layer on. So we're hosting here one of our alert fire cameras. We've got air quality on this hill. We have radio repeaters for emergency events. And then tied into all that and those radios there is our network of these sentries, these weather stations all over the preserve. So to nail in on some of the key aspects of a Sentinel site, and I hope my screen's not in your way too much. What do Sentinel sites do? The most foundational piece is capturing this long-term record of both the drivers and responders to climate change. And we're going to dive into that in some detail. What are these drivers and responders? But it's that long-term record that is so foundational. And there's an awful lot of work that goes into maintaining that long-term record and keeping an eye on it in QA, QC, quality control on that. And from that long-term record, we develop baselines against which to compare change. If, for example, if you go outside today and go, ooh, it's really hot today, relative to what? It begs the question. Well, you have, whether it's anecdotal evidence, and at a Sentinel site, it's our long-term data records. We have that baseline to compare against. So if we're talking about climate change, you kind of get a sense it's happening and you see these events, but you really need that baseline to push forward rigorous defendable science to then implement change. And so what these baselines are these time series data sets that allow us to examine the trends, trajectory, and velocity of environmental change. And that's a critical piece because we live in a world of finite resources, whether it's funding, time, and so it's important to prioritize the actions we take, the stewardship, the adaptation efforts, the restoration efforts. And so not only to understand which way are these trends headed in both the drivers and responders, but how quickly. And that helps us prioritize, where do we need to take action now, or how do we adapt, whether we try to help guide Mother Nature in a certain direction on the landscape, or if we just have to get out of the way. And so utilizing those historic records and even the stuff we're collecting today, right now, and here's the important part, is we can begin to predict and model these future outcomes. Because if you go outside and it's already blazing hot, well, you're already in it. There's not much you can do except go back inside. But if you can start to understand, like, hey, for example, we've warmed up 3 degrees Celsius, and I'm making this up, 3 degrees Celsius in the last 10 years. And so you go, okay, but on that hillside, I see fewer and fewer trees. We have the data at a Sentinel site to go, yeah, there are fewer trees there. There is diminishing biomass. And we can go, well, what species are diminishing? And then furthermore, we can go, all right, well, we see with every 1 degree increase in temperature, we have this much fewer, for example, fir trees. And so we can project and go, ooh, in about a couple decades, there may be no more fir trees on that hillside, which means that's no longer a suitable habitat for XYZ, a lot of our wildlife that live in that environment. So that's the critically important piece here, is to make that step from like looking at the data right now to understanding where we're going to end up in 10, 20, 30 years, the end of the century, stuff like that. And here's another critical piece of the Sentinel site is we retain data and the ability to answer questions that have yet to be conceived. And this may be a common occurrence in other fields, but I have to admit, I've spent some days in the field where it's blazing hot and you're covered in ticks and poison oak, and you go, what's the point of this data set? What's the question here? Just like, oh, and then you're just kind of out there sweating. And then I remember, you know what? That burning question, maybe, this is hyperbole, the one that saves humanity has yet to be asked. And when that time comes, Pepperwood and other Sentinel sites, we may have the data to answer and address that question and make some really, groundbreaking finds and help inform decision makers and policy and land stewardship activities. So I mentioned Pepperwood is just one site. There is a tremendous amount of work being done right now, and it's kind of a relatively new phenomenon. I mean, how long has the internet been around in a meaningful way, and our ability to network both people and data, and also all these extreme events that we see, right there on the front page, or we experience in real life, wildfire, drought, flood, epic hurricanes. I mean, just think of like the last couple of weeks on the East Coast. All of that stuff, those are the extremes. And so Sentinel sites really work to capture the in-between, and we can see it in the data all along. But the thing is, is as diverse Pepperwood is, California is equally diverse. And so there's this need to capture all the different ecosystems, and not just, Pepperwood, but the entire state. And in essence, make California a sentinel state, because climate change manifests itself in so many different ways across the state. If you're on the coast, it might be all about sea level rise or fog events or ocean currents and temperatures. If you're on the crest of the Sierras, it might be all about that snowpack and diminishing runoff, which means diminishing recharge in our aquifers through our Central Valley, which, to make the entire leap here, means reduced agricultural or higher prices for our economy, and agriculture is so pivotal to what California is, and we feed so much of the world with what we do here in California, that there's huge ramifications worldwide for what's going on right here. And so we have recognized the need, like, what, we need to understand what's happening across all the ecosystems of California. So there's this effort by the Climate Biodiversity Network to create a Sentinel site network. And in doing that, the aim is to figure out what are our core set of protocols, measurements, standards that we all adhere to, so that we can begin to do these regional analysis, so we can understand the gradients of change. Where are things changing rapidly and how? Where are they not changing so much? And that also gives us the ability to start to think about projections of habitat suitability, and, like, for example, like, ooh, it's getting too warm here at Pepperwood for our bears to persist. They're just not, they don't live in this kind of environment. Where in California might they thrive and survive under a changing climate? And so you can do these habitat suitability and migration maps, and you can start to at least make informed decisions around policy and management. Like, what actions can we take? Well, science will tell you what actions are possible, and then it's up to the human component to decide our values and what actions to take. So there's a lot of human component to all the science we're doing here. Moving forward, I've mentioned these drivers a few times. So now we're going to talk about the drivers of change and the responders of change. So I've used the term abiotic. That's sort of these non-living, not biological, non-living variables. So I immediately go to meteorology. Think of temperature, rainfall, relative humidity, solar radiation, even in a sense, your soils and your hydrology, but we'll touch on those in the next slide. So we measure all of those things, and those are our, very discrete 15-minute interval time series that allow us to build that long-term record and baseline. But another driver are these disturbances that are, one, sort of a response to some of these, but also the disturbances are kind of like the catalyzing events that that make these dramatic shifts rapidly across the landscape. And these are things like wildfire, prescribed fire, thinning, grazing, and restoration. And I pause here because this one always trips me up a little bit. You go, well, prescribed fire, thinning, grazing, restoration, those are like human things that we're doing. That's correct. But it's important to note that, and I mentioned this early on, we are part of the natural world. And for thousands of years, it's known that native peoples coexisted in this natural world. They lived with the environment and they stewarded the landscape. And prescribed fire was a huge tool in California, and I'm sure elsewhere. And so our species, our landscape, our ecosystems, our wildlife co-evolved with that disturbance regime. And so we're doing a lot of work now to try to bring that back, because a prescribed fire is a scalable tool. And we also have, if you look at the species out there, our oaks are notorious for doing well in fire. We have knob cone pines that are serotinous, meaning they need fire to propagate, to open up their cones, to drop seed, and then, establish recruitment moving forward. Another thing we use, and it's a driver of change, is our grazing. Like, well, we're putting cattle on the landscape. There weren't always cattle. That's true. But what we're trying to do is mimic what we believe were historic herds of grazing animals that would have been on our predominantly native perennial, meaning the grasses don't ever die. They grow into a clump, and they may dry for the season, but they come back every year. Our grasslands co-evolved with grazing. And just like if you have a lawn and you mow your lawn, well, it grows right back. It really thrives under, being mowed in that disturbance regime. And so our native grasslands that used to be predominantly perennial honestly thrive under grazing. And it kind of knocks back the perennials, because if you graze those perennials before they drop seed, well, they're not going to sow seed. They're done. But our perennials really co-evolved. Our grasslands co-evolved with some sort of grazing. And let's jump forward from there. So the responders to change. And let's start with the soils and hydrology piece. There's kind of a bit of a chicken and egg thing going on here, but the hydrology and the soils, those are, in one sense, responders to those initial drivers, the meteorology, but they're also drivers on the biotic side, on our vegetation, our wildlife, our flora and fauna. So for example, if we get a lot of precipitation, that has ramifications for our hydrology, and anything that's tied into hydrology is tied into the water balance and the water cycle, including the soils. All right, so the image here in the bottom left is some stream gauging to measure flow that we do at Pepperwood. And this is following one of those atmospheric rivers, and we're going to talk about those more. But to plant a seed, something to think about, and I may ultimately leave you all with more questions and answers. And honestly, that's just good science. This is following an atmospheric river. You may, moving through time, see that, the average precipitation isn't really changing. But there's this idea, and we're seeing it, that climate change is pushing us towards the extremes. So while the average may, maintain the same, we may have our precipitation delivered in 3 huge atmospheric rivers, and that may be 30 inches. Well, if that happens on a landscape, so much of that water runs right off that landscape into these creeks, into the Russian River, and then out to our, larger tributaries and eventually the ocean. And so it doesn't have this effective infiltration into our soils. And so our soils remain drier. And here's the tie. What's rooted into our soils? Our vegetation. So now we're looking really at these ultimate responders, our ecosystems and our vegetation. So in the upper left there, we're looking at a fir forest, Pepperwood, and we're actively doing a prescribed fire in there. So that's smoke coming up through there. But if that fir forest got established under, we receive this much rain a year and this much of it gets stored in the soils, and that's enough to grow and propagate and put more seeds and sustain this forest. Well, if the precipitation changes such that so much of it runs off into the streams and the soils don't wet up like that fir forest is used to, suddenly, if those trees don't just die outright, they are far more stressed and far more susceptible to things like wildfire or bark beetle or fungal attacks. And if those fir forests go, well, certain species, including the black bear, those fir forests are really thought of as nursery regions. They bed at the base of larger fir trees. They send their cubs up in case of danger in those fir trees. You can literally go through Pepperwood and go big fir tree to big fir tree, and you will find bear scratches and beds. So there's a connection there. And other things as well, if there's a devastating wildfire that comes through, or even our management activities, and it alters the environment in such a way that there's not as much forage for our not exactly grazing, but herbivore species, our deer. Well, if the deer change, the mountain lion follows, because deer are the primary prey source for the mountain lion, and those things begin to shift and phase out. And the question is, where are they going to go? And we do an awful lot of work to identify corridors about how these animals might move across the landscape and look for regions that may be more suitable for them to live. Just about like we were talking about, assisted migration is the term. It doesn't always roll off the tongue so nice, but where are these species going to persist in the future? Where could they persist? And we're trying to identify that through the use of sentinel sites. And here's a really key one, looking at the wildlife here, are pollinators. They kind of go unseen because they're just tiny little bees and flies, and we have so many different native bees that are even smaller than the honeybee. Those co-evolved with a set of climatic conditions and this environment. And being so small, they're some of the most sensitive things to a warming climate or, deluges of precipitation. And if they go, well, they're the same critters that pollinate all of our vineyards and our crops and our orchards and so much of the economy that is key to both Sonoma County and California as a whole. So there are huge ramifications, starting even at that smallest end of the spectrum of wildlife out there. Okay, Sentinel site tools. What are some of the tools, the tricks of the trade here? I didn't dare crowd this page out too much because I could put an awful lot of pictures, and this is just kind of an overview that doesn't include everything. First and foremost, the upper left there, the weather station, and it's kind of the ubiquitous piece. Lots of weather stations out there, but I mentioned we're trying to hit a set of standards that makes this data comparable to the next Sentinel site over to the next one and the next one. And those just run in perpetuity, and you've probably passed way more than you've ever noticed. And if they're done right, they kind of just blend into the environment and they just run out there. They are the sentry on the Sentinel site. They run in perpetuity, no matter what I'm up to. And then moving left to right across the top there, this next photo here is a drift fence that we use. It's got a downward facing camera in that little green housing. And we do an awful lot of monitoring with game cameras to capture megafauna. So deer, coyote, bobcat, bears, mountain lions, that kind of stuff. But those smaller critters, things, rodents, snakes, lizards, you don't really pick them up on the game camera on a post. And so we want to understand, I mentioned even the bees, every size, class, and clade of animal and wildlife out there. And so we implement this to track some of those smaller vertebrates as well. Moving over, we do stream gauging at Pepperwood, measuring the actual flow. This isn't just stream height, but this is flow. This is gallons per minute. This is cubic feet per second coming out of our streams. And understanding how a system responds, so this is at the bottom end of a sub-watershed of the Russian River, which is a much larger watershed. But if we can understand how these sub-watersheds respond, something manageable that we can actually instrument and get our hands around and our minds around, we can then extrapolate to larger watersheds that suddenly have very, very meaningful, they're very meaningful for agriculture in Sonoma County. That Russian River runs right through the heart of the Alexander Valley and is critical to everything we do in Sonoma County. We monitor fog. We're here at the inner extent of fog that comes over the Coast Range. We monitor here at Pepperwood. We are at the inner extent of our coastal redwoods. So kind of here on this pivotal frontier of like, if things begin to change, we're going to, with respect to redwoods and fog, we're going to see it here first. And then moving to the bottom left, and this is underrepresented here, so much of what we do comes down to highly trained people in the field taking these measurements. Because if you think time series data sets from data loggers are difficult and messy enough to deal with, the natural world, the biological component of all this, the responders are the messiest of them all, right? They don't always behave like you predict, and new species show up and things change rapidly. So this is Michelle Halber here, was our preserve ecologist, now manages all the ecological research that takes place on Pepperwood, looking at forest recovery in the herbaceous understory post-prescribed burning, because we want to understand how is our management affecting the natural world. Moving across, we do an awful lot with soil moisture, and soils are kind of the medium that links the abiotic to the biotic. Our vegetation's rooted into it. And so we operate things like a neutron probe. We measure soil moisture down at 24 feet deep in the root zone. And we can start to think about, okay, are we seeing aquifer recharge? And we have, I think it's like 170 soil sensors in these stacked arrays here, measuring soil moisture in the upper meter of the soil. And then finally, I'm sort of the abiotic guy. So I have to always give a shout out to the ecology and the biologic side of everything we do at Pepperwood. We have so many forest plots, thousands of tagged trees out there where we take all these metrics of forest biomass and response to climate and response to our prescribed burning and thinning. And so this is myself and an intern taking the DBH, the diameter at breast height of that tree, which you can then use to calculate biomass and understand how is this tree growing, how is this tree responding. Okay. We're going to make a pivot here. I'm going to actually show you guys some data. And these are the numbers between the extremes, all right? And I want to point out this is not a doom and gloom thing at all. Like, we've seen the floods, we've seen the fires and the hurricanes, wherever you are, there's some craziness going on. But Sentinel sites offer that glimmer of hope in that, you know what, we can see the approach to these extreme events. And so we know it before it's going to happen. And that gives us the ability to adapt, get out of the way, or address these things, or guides our management and stewardship strategies. How do we prevent these things from happening? Or adapt around them, right? Okay, so here it is. Key to a Sentinel site, this long-term record. I better move this out of the way. All right, this is the most ubiquitous data stream you're going to find out there, temperature. And oftentimes it's not the most exciting one to look at, but you can do some very cool things with this. To orient you to this figure, we have temperature on the left vertical axis there in Celsius. We have time across the bottom. And I'm remembering now, and I really apologize if you're colorblind, but I'm going to walk you through what we're looking at in this figure. I've broken the temperature record down into 3 distinct pieces. We have the maximum daily temperature in red. That's the top portion of the graph with those labels on it, which are in Fahrenheit, not Celsius. We have daily minimum temperature. That's the bottom section of this graph in blue. And then we have the average in green right through the middle. Laid over top of these data sets are trend lines, just linear trend lines. And they correspond in color, red, green, blue, moving top to bottom to your maximum temps, your average temps, and your minimum temps. Okay. So keep in mind, this is one station on one Sentinel site in Northern California. But what is one of the first things we see? Temperatures trending up. There it is. It's global warming. There's the proof. Pause. It's not the proof. Any rigorous science, like I've mentioned before in this earlier, you have to evaluate everything at a regional scale. And the idea of global warming, I'm certain you could find places on the face of the earth where things are actually cooling down and go, oh, and you even hear from some folks who go, oh, I found a snowball in July. I'm like, well, pause. We are looking at the global average and looking at all these different stations in these different ecosystems all over the face of the globe. And we look at those on an average basis. Yes, we see temperature increasing year after year around the globe. So, with due diligence and scientific rigor, you would want to go look at more stations and represent the whole ecosystem that is Northern California before you jump to any conclusions here. That said, there are some very interesting things already going on in our short record. I mentioned, long-term record. Pepperwood's first weather station went in 2010. So that's 14 years of data collection. That's not a very long record. I hope to be doing this for quite a while. So maybe by the time I'm ready to retire, I can see some really cool trends. But that said, there are some very interesting things going on. This box I've thrown up here on the screen, look at the first half of this record. For that first half, those first, 6 years, that station never broke 100 degrees. And you may be thinking, wait, I live in Sonoma County. I was here. It was definitely over 100 degrees. This station happens to run cooler. And that just speaks to these dynamic places and ecosystems, even over short distances. And so you have to look at the average of a lot of different stations. But here's one of those things. I may leave you with more questions here than answers. So what's going on, right? If we look forward, what happened? How all of a sudden we have these, we've increased the average temperature across these two timeframes by almost 10 degrees Fahrenheit. And we're seeing these record temperatures, 105, 107, 112. And I live down in Windsor, and I remember it being that hot down in Windsor. I'm like, oh my gosh. I don't have the answer here yet. But as a Sentinel site, we continue to track these things. And is this, the question is this a little blip in the overall trend, or is this going to continue? But another thing you can start to ask, and even looking at this pretty simple data set, is like, okay, I see this record-setting thing here, and we want to think about the responders. This is the driver, the abiotic here, this record-setting heat wave here, but there's just one of them in an otherwise pretty cool summer. And then you go, I wonder what effect that had on the natural world. And then if I told you, well, this summer hasn't been that hot, that's in one sense true, but you might say, wait a sec, it's been blazing hot all summer. I've lost my cursor, but over on the far left-hand side of this graph, we've had 3 distinct heat waves this summer. And so you start to question, is there a duration component to affecting, driving response? And so these 3 sustained heat waves, that cumulative impact may have much more of an impact than even one single huge heat wave. Anyway, so we don't know yet, but we have that data to then address those questions in the future and examine this stuff. And as we start to put more and more of these data sets together. So as we move forward, I'm going to show you a few more graphs. I'm trying to make the link here and walk from the abiotic all the way through the biotic side. So what's next in this scheme? Soil moisture, right? That medium that really ties together the abiotic and the biotic world. Where can I put this thing? So let me orient you to this plot. We have relative humidity and temperature on that left-hand axis. We have soil moisture, that black line plotted on the right axis. Relative humidity is in blue there. Temperature is that orange color. Okay, so let's interpret this soil moisture curve. And this is soil moisture in a grassland environment at 50 centimeters down. So that's quite a bit of soil over top of this sensor. This begins just this last spring, and the record goes before that, so I've just taken a subset here, but April 1. So we're coming out of winter. It's early spring. Our soils are essentially saturated. So that's that high plateau. When we get to early May, all of a sudden, things start to warm up. Our grasslands begin to explode. Everybody's buying plants to go plant in their garden. It's that time of year. Everything's growing rapidly. And as those plants turn on, photosynthesis begins to occur, and evapotranspiration. Plants are utilizing water, pulling water up through their roots. They start to draw down that soil water. And so you see the inflection in the curve and the rapid drawdown. And those bright green hills that you see suddenly become those iconic golden hills of California as you approach early June. And there's another inflection and things start to taper off. And this is the exact same time that you see all the annual grasses starting to senesce. They are done with their life cycle. And even the perennial grasses are starting to turn brown for the season because the water's been drawn down below the root zone, potentially. And for most of the summer, you enter this linear downward line, just subtly dropping again and again and again. But there's really not any more plant utilization here because all the stuff is senesced for the season. Now we get into fire season. So now we're starting to tie it, this is what hits home for a lot of people. There are these fire weather windows that open up in these data sets, and the name fits perfectly. Literally, there's a window in the data set. So it's late summer, early fall. We get high temperatures. They don't have to be brutally hot, but high temperatures and low relative humidity, single digits. This, if you go back in time and plot the same data set over the Kincaid fire or the Tubbs fire, and I'm certain many, many fires throughout California, this is where those fires occur. And one of the missing ingredients here, because it would make the plot too messy, if you put a wind event in that window, it is scary how predictable a fire ignition and event is under those circumstances. All right, but back to the soils piece. Check it out. In the middle of this window, soils just continue to dry down at a normal rate. There is a lag here, right? So we may have exited this fire window and be like, okay, the probability of an ignition is down. We just don't feel like things are going to catch on fire now. But following that window, we see this downward inflection in that black line, the soils there, and an already bone dry landscape becomes even drier, and those soils are drawn down just a few more percent beyond, if you're a plant person, the permanent wilting point, the point at which plants can actually pull water out of the soil. And there's always still water in the soil. It's just held so tightly and there's so little of it that plants can't extract it. So it's evaporation alone from those extreme temperatures and low relative humidities that is continuing to pull moisture out of the soil. What's rooted in our soils? The biotic world, the vegetation. All right, the graphs continue to get busier. So let's walk through this one. On the left-hand vertical axis, we have temperature and relative humidity and soil moisture, which I arbitrarily multiplied by 2 to make it plot out nicely, but you're going to see the story here. On the right-hand axis, we have live fuel moisture as a percent. And, we can track, we use live fuel moisture in this case to look at fire severity, but you can model these things as well. The 3 species that we're looking at for live fuel moisture in this particular figure are all chaparral species. So they're toyon, that's the blue top line. Leather oak is orange there in the middle, and it's not a tree in this case, it's a shrubby leather oak. And then chamise, that's that bottom green line. Historically, chamise is the indicator species of choice used by firefighting agencies, CAL FIRE, to set those signs that you drive past on the highway. Fire danger today is low, medium, high. A lot of that comes right off these measurements of live fuel moisture. Okay, so we mentioned a lag between these fire weather windows and soils responding. And so now the question is, is there a lag in the vegetation? And that matters because you may think, oh, we're out of fire weather window. We're out of this, high probability of ignition. But if the landscape and the vegetation continues to dry out, the severity and the potential for like a runaway wildfire still exists. And even more so. And that's important because when first responders have to decide, where do we make a stand? Where can we fight this fire? And they look at a hillside over there and go, that fuel moisture, there's no stopping it there. So it helps prioritize what resources, where to place those resources. And ultimately, it's protecting lives and property in the communities in which we live. But I mentioned this lag here, the lag in the soils. Now check this out. And we sort of lose the resolution here. It's not 15-minute data. We go out and collect live fuel moisture by hand every 2 weeks across the summer. And so we don't exactly have the resolution between those 2-week intervals. But right here, we took a measurement in the middle of this fire weather window. And so you would think like, oh, it should be really dry there. The plant should be just nose diving. Well, there's a lag time. that upward trend just preceding that fire weather window, we don't see it in Toyon, but we see it in leather oak and chamise. Well, that's in response to the previous weeks in which we had pretty high relative humidities and not that extreme temperatures. So those plants actually recovered a little bit. They were able to keep up with the evaporative demand. And this is hot off the press. Those last points there on the left are from just 2 days ago. And I thought, you know what? I bet there's something going on here, just looking at the patterns. Even outside of this window, those final points 2 weeks later responded to this dry event, and we see this drastic drawdown. Now, Toyon isn't playing along nicely, and that's what keeps me coming back and doing science. Why is that? There's another question. But in some of our indicator species here, we do see that dry down. All right. And I want to talk about precipitation as well. And I mentioned this a little bit earlier. You know, a lot of it depends. So think about atmospheric rivers and the effective precipitation on the landscape and the recharge on the landscape and combating landscape level droughts really has to do with how did the precipitation arrive? You know, was it atmospheric rivers or did it spread itself out? And so this figure here, on the left-hand axis, we have water year total precipitation. I forgot the legend, but those are those pink, purplish, wider bars. That is the total water for that water year. That's October 1 through the following September 30th. And then those dark blue lines represent daily precipitation. That's plotted on the right-hand axis. And I've called out in those labels atmospheric river events where in 24-hour period, you know, we're seeing extreme amounts of precipitation, and that's what creates a lot of the flooding downstream. And so if all the water is flooding out and running out to the ocean, it's not effectively recharging the landscape. But something, you know, that hits near and dear for people, we can have, you know, very good water years. For example, these last 2 years, well above average, but we didn't see any flooding in places. We got awful close, but in places like Guerneville, lower in the Russian River watershed, of which we are a part, we didn't see flooding because the rainfall was spread out enough. And it's those years that allow for a lot of recharge and a lot of that water to infiltrate the soils. Other years, you know, we didn't necessarily get a lot of rain total there in that 2021 window, but there was an atmospheric river in early October that delivered over 4 inches of rain. And we ultimately saw some flooding from that. So I think I have far surpassed the 30-minute mark. And I'm likely have left you with more questions than answers, and that's okay. I continue to have questions every day. And so I really appreciate you all sticking this out with me. And hopefully there's some time left to address any questions you might have. So thank you.
That was awesome and super informative, Ryan. Thank you so much. We do have quite a few questions here.
Oh boy.
Yes, I know. Get ready. This is the best part. So, okay. Right. Let's get started here. So number one, this is not a question. This is from Morgan Abbott. He says,
Oh boy. Hey,
on the
Morgan.
Soils publication. So thank you, Morgan, for that. And it looks like the chat is turned off. Dang, I don't know why it's doing that, but at least the question and answer box is still working for everybody.
Okay.
So I do have another question. Do you have plans to implement beaver dam analogs for water storage for fish and wildlife?
That is a really cool one. As a matter of fact, there's a magazine that someone came up with, and I just read the other day here in the office. We have had folks out looking at where we might place analog beaver dams or even introduce beavers. I don't know if that's going to happen, but up here on Pepperwood, because if you can, if you can slow it, spread it, sink it, and get all that what could be floodwaters spread out to slowly infiltrate into the uplands, well, that supplies all your base flow late into the summer. So the Russian River is not so like slimy and grody come like August. I see opportunity for that in lots of different places in California, especially with certain dam removals. Like if you're familiar with the Eel River and taking out the dam at Lake Pillsbury, that it's got a lot of sediment in there, and it just seems like an ideal location to bring beavers. Whether it's beavers or analog beaver dams, whatever mechanism is going to allow us to slow down potential floodwaters and spread it out on the landscape and recharge that landscape. Yeah, we're considering it. We try to even do it, we think through our grazing and our restoration activities to prevent erosion and gulling. We really want to slow down those floodwaters and give them time to infiltrate. And that's a huge benefit for both the ecosystem and downstream, like less flooding for where we live. So yeah, that's a tool that we haven't used yet, but it has been considered, and we have had people out here looking at that very question.
Great answer. I didn't know that at all. It's very interesting. Okay, so I do have more of a comment here from Stu Weiss. There are so many data being collected and funding for collection seems to be decently funded, but analysis of the voluminous data is shortchanged in general. I have lots of ideas for innovative analysis, but finding the funding is actually do the analysis work well is a frustrating process.
Yeah. Stu knows the struggle for sure.
Yeah.
Every time I sit down with these data sets, I wish I could tell you this is part of what I was doing every day, but there's so much work that goes into maintaining a Sentinel site. But every time, and I'm supposed to have the pulse on the data set. Every time I sit down with the data set, there's another amazing discovery, like, ooh, I didn't know that happened, or like, look at this pattern. And then I search around the office, like, who can I tell about this? So I hear you, Stu, and I would love to do more of that and agree that finding the funding to follow through on a lot of this is something we need to work on.
And he also noted that there was one point at which he believes you misspoke, annual versus perennial grasses, he was just noting.
Yeah, you probably caught me there. Yes, we have native perennial grasslands, typically are bunch grasses, and we are heavily invaded, as is most of California, with these exotic annual grasses, the ones that make all the stickers that you can throw at people. Yeah, so thank you.
Thank you for qualifying that. And then Morgan Abbott again, what variables that are being monitored are replicated across Sentinel sites? Great question.
All right, so that's a good one, and even recent discovery on my part too, but it's pretty recent that the California Biodiversity Network has gotten together to try to hone in on that. And I've heard it, because it really does come down to the nuts and bolts, like how many weather stations, how far apart, how high do you set the sensors, what sensors? So in a general sense, I've heard it stated from some folks in that group, well, it's basically all your classic weather parameters. So temperature, relative humidity, precipitation, wind speed and direction. And definitely there has to be components in a Sentinel site. This seems to be one of the criteria that's coming out that capture both the abiotic and the biotic side. So things like acoustic monitoring for bird and bat diversity, camera traps, whether it's game cameras like we have, but also downward facing, so you capture the whole spectrum of critters in the landscape. There has to be that, you have to monitor both the drivers and responders. Beyond that, they're still working out the final nuts and bolts. And also, every site has something so unique to itself. So a lot of what we do at Pepperwood may not apply to another Sentinel site. So yeah, honing in on that core set of measurements, which may not be huge and expansive. Anyways, that is the first pivotal step.
Okay, next question. With regard to Sentinel sites, is there a mapping process to identify locations that are closest in nature to the Sentinel sites?
Is there mapping? So what I think that question is like, is there a tool out there that says, that would tell you like, oh, this Sentinel site is very similar to this Sentinel site, like what ecosystem they'd be capturing? Is there a mapping tool? Certainly you could do it through remote sensing, and there's also, having to fund all that. But if you can do things like LiDAR that tells you what the elevation is, how it changes, and if you put weather stations out there and have an idea of what's the temperature regime, what's the moisture regime here, and if you're lucky enough to get like a hyperspectral flight done by aircraft, maybe not satellite, you can start to look at what different vegetation communities are out there. So this makes me think of, we have a lot of oak species here at Pepperwood, and they seem to do quite well. Well, Morgan Abbott hosted this conference. If you're looking at oaks in other parts of the state, think like the Sierra foothills and blue oaks. Well, there's some places where those species are really struggling as things continue to warm up there. And so you might look for, you might look for a place, a sentinel site, a protected land of some sort where these species might flourish, because we do want to do our very best to protect and maintain biodiversity, because there's so many like ramifications in there that we don't even really know about. Like, if the blue oaks go, well, what species really relies on that? Is there a pollinator involved? And so there's some cascading effects that are a little scary that I don't think we totally realize yet. Hopefully that sort of addressed the question.
I think that's great. Thank you. Okay, so this next question gets at the intersection of sort of weather and climate change monitoring and agriculture. So
Okay.
this is a good one. So this question is, how does your weather station differ from a CIMIS station or a California Irrigation Management Information System, for those who are wondering?
Oh boy. All right. No, I never tell people what I don't really know, so I'm not going to tell you. I definitely know that answer. I think there's mostly overlap there. I think that SEMA stations, I mean, honestly, y'all could probably Google it and come up with a better answer than me right now, but I think they do a lot looking at evapotranspiration and using the Penman-Monteith equations to figure that kind of stuff out. So there's a lot of overlap there. But I'm not gonna trick you. I don't know all the differences. I couldn't list that out for you. But I'm familiar with them to some degree and have relied on them in the past, even throughout my earlier career in grad school to be like, I need some data from here. And if you can tie the monitoring to agriculture, which is tied to the economy, I mean, there's a great mechanism for funding, and it's critically important. Yeah, for just sustaining not only the natural world, but everything that we enjoy as well. So that's a little bit of a weak answer there, but I appreciate the question.
I think it's a strong way to answer if you don't know, to not make a bunch of stuff up. So
Yeah.
well
There's
done.
always more for me to learn. That's what keeps me coming back. Like I've had to learn in this career to be comfortable with not knowing what I don't know. That's just the next benchmark. Like I'll probably go Google SEMA station right after this. So all
Cool.
good.
Okay, so we have another question here. Is anyone looking at the collective Sentinel site data across California, and are the data collection methods standardized?
Well, I want to say people are trying, and I think the need is really recently being recognized. I've practiced this so many times I can't be sure what I already said, but the advent of the internet's only like a few decades old, and the ability to network both people and data and bring those things together to do these analyses is one kind of recent, and even the ability to do it. And now we're realizing like, ooh, we need to do that because we need to understand how climate change is acting across all of California. And so I think folks are working on that, and there's a big push to work on that. And this California Biodiversity Network is sort of spearheading that effort. Like, hey, where are these places? Who are the organizations or the property owners or whatever it is, these places that represent all these different ecosystems in California? And we need to first and foremost make sure that they are collecting data in a similar way or standardized way so we can make these comparisons. I think that kind of is the next frontier, and hopefully we get good at it and move quickly enough that we can start to get ahead and adapt to some of these changes. And I certainly think that the remote sensing crowd, using satellites or modeling. So I'm thinking of the USGS and Lori and Alan Flint in particular in the basin characterization model. You can start to do these larger regional analysis, but before those analysis, you need these ground validation and truthing points, and that's so much of what Sentinel sites are. So I think it's happening, and I think it's accelerating. This is my answer.
Okay, this next one is actually more of a comment, probably in
Okay.
relation to what we were talking about earlier with the beaver dam comment. So Paul has mentioned that they have many beaver dams along the Napa River watershed that can be seen.
Oh,
So interesting there.
neighbors. All right.
And another comment here from Harrison Dwight, grandson of Pepperwood's founders, Herb and Jane Dwight. Thank you, Brian, for a very informative seminar. Thank you, Harrison, for joining us today.
Thanks.
And then another question here, which I think you're going to like. All right. What instruments do you use to track fog events?
Oh, okay. This is a good one. All right, so fog is really cool, but sometimes it seems to struggle to get a lot of funding. We are actually working with some collaborators down in Chile. Basically, this across the equator study at similar latitudes. Did I get that right? Because they have a lot of fog down there, and it's pretty critical it's like their only input on that plateau over the Andes, and we have fog here. There is work, just like standardizing across Sentinel sites, to standardize fog collection and monitoring methods. At Pepperwood, and elsewhere. This is sort of the standard. It is the standard. It's a 1 by 1 meter mesh of material that when the fog blows through, it condenses on that mesh. The mesh captures it, condenses, and trickles through to a trough, and then goes through a standard tipping bucket rain gauge, and we measure the fog. That mesh material, this is kind of in the weeds, but it's a 35% shade coefficient double Rachel mesh. It's essentially shade cloth that you would use in a greenhouse or over some plants. It has to be set, 2 meters off the ground into the prevailing winds. That's kind of the bare minimum. But actually, I had a Campbell Scientific. They make a lot of sensors. Their rep was out here yesterday, and they're like, "Oh man, you guys should get a visibility sensor because fog is an entire spectrum of like it's raining to it's this very light, dry fog." And so if you begin to, there's so much you can do there. You could add in different sensors and start to tie, hey, if we know we can see this far, how dense is that fog? And if we know the wind speed, well, what's the flux of water vapor moving through that mesh? And ultimately, fog's so important around here because it's our only source of relief in our dry summer months. Like we think of a fog season from May through the return of rain. So we're sort of coming up on the end here. And, it's kind of the only thing sustaining some species through the dry summer months. And there's more to be done there. It's really hard to model fog because it's like 3-dimensional in space and time. And it comes from different sources here at Pepperwood. It might, in this last image here you're looking at, that's the Napa and Knights Valley behind us. The ocean's not that way. The ocean's the other way. Sometimes the fog comes up from that direction and it may have a different chemistry. It may have a different droplet size. Other times it's coming right off the coast behind this image. And, it's a different source. There's a lot to do with fog chemistry and then trying to model and understand fog. And then Pepperwood right now, we are just quantifying fog. How much are we getting? That was rambled, but I'm always excited about fog. So I'm always game for more.
Thank you for that, Ryan. Okay, so there's two, well, this one's sort of, there's a statement and a related question, both about AI. Rick mentions that Pepperwood would be a great place for AI, and there's an incredible complexity there. And then we have an anonymous attendee who is wondering how AI is being introduced into our work.
Okay. Here's another one. I don't know enough about AI except for I see it pop up first in my Google searches now. But I think there is a tremendous opportunity with so many data set. Like it's just mind-boggling. Even if you're doing R and some really heavy duty modeling, like that's a full-time job and career. And so it's my understanding. I think AI might play a pivotal role in like rapidly looking at all these relationships and data sets and then determining where are things headed? What do we expect? So if there's someone out there, Rick, interested, Pepperwood's a small team and we're always looking for ways to innovate. And so much of what we get done comes from folks helping out, whether stewards or volunteers. And we are starting to move that way with the science as well. I just work with people who can offer different data management and ideas. So I think there is a role there, but I just don't know a whole lot about it yet.
Okay. Are there any sap flow sensors deployed at Pepperwood?
There ought to be. I get asked that question all the time. So the answer is no. But something we do, right? I mean, there's a great link right there between the soils and live fuel moisture and stress in the trees. We do have soil sensors installed into the trees, and you actually see a diurnal pattern of when trees uptake water during the day when the sun is out, and then the water seems to settle out. There's actually a pattern there, and that was brought to us by the USGS, trying to understand how L-band radar was related to moisture we're seeing in the environment, particularly soils. But then they realized, oh shoot, 70% of Pepperwood's covered in trees, and so we're really measuring some artifact of live fuel moisture. So we thought, let's throw some soil sensors in these trees and see if we can't tie soil moisture to tree bole moisture to live fuel moisture that we were pulling out. Yeah, a sap flow sensor, we should. I will keep it in mind for the next funding opportunity that comes through.
Awesome. I didn't even know that there was such a thing. Are you looking at berms and swales with respect to effectiveness in slowing, spreading, and sinking water from huge storms?
Are we looking at berms and swales? Well, specifically from that lens, maybe not. But I will say that we have a handful of ponds up here at Pepperwood. And all of those ponds are there because in some historic time, wasn't native peoples, but homesteaders out here, they pushed up berms to make all these ponds, probably for cattle and irrigation. And certainly those are great pockets and pools of recharge. We look a lot at trying to control erosion. So that might be getting at the same thing. Like if we can keep, if we can keep our waterways from being eroded and channelized, that helps to slow down that water, just get it to move through in pools and trickles. And like, I think we get better infiltration out of that and better recharge. And soils, they are renewable, but only on time scales of like 100,000 years. So if you lose your soil, if it gets washed away, that's no good. So that sort of touches on that idea of how are we promoting infiltration with berms and swales. And I think there's probably, back to the beaver dam thing, better opportunity. Pepperwood is a living landscapes, the cliche phrase, but we actively manage the preserve, right? We don't just stand back and say and just like let it go. We have an adaptive management plan, so we're always game to like try these things, and then we bring the science to follow, and then we can evaluate, did it have the intended effect we wanted? If not, how would we tweak it so that we do get that intended effect? So I think Pepperwood's the place for trying those things out.
And a not unrelated final question here from Morgan. Since you installed the two weirs, have you noticed a difference in stream bed scouring between above and below the weir? It looks like they're creating bear habitat.
Yeah, it's some bear habitat. Those weirs, lots of hard lessons learned, but they're very cool. Not a lot of people do them in this environment because we have ephemeral streams, and they go, so I think that means they go dry. They go from bone dry to 4 feet of water in one event. And so it's kind of hard and dynamic environment to put instruments in. Scouring. We put these stream gauging stations on consolidated bedrock. So they're not just sitting in this ravelly, bouldery stream. So there's not so much scouring when that water comes over and hits that bedrock. It definitely blows sediment out right there. Most of the issue is retaining sediment behind the weir plate. We do have blowout tubes down low. We got, no one tell on me, we got all the permits from CDFW and the Water Quality Control Board, stream and lake bed alteration stuff, and said, hey, we're going to install these tubes. We can open them up, let the sediment through, and that's what we do. Honestly, both up and downstream, Morgan, and I think it's year to year, but right now it just feels like there's more sediment both up and downstream because it depends when I open those tubes to let the sediment through. If there's not another storm to follow that release of the sediment, it kind of just parks itself downstream. And so we are, and I don't know if it's great, but have these packets of sediment that move through, and that's a lot different, I suppose, than if it all came through neatly and spread out. I don't want to say there's a whole bunch of scouring yet, but it's something I have to keep an eye on.
Awesome. Well, that is it for our questions here, and we're actually at the hour, so this is excellent timing all around. So I want to thank you, Ryan. This was super informative and really enjoyable, and I want to thank everyone for joining us today. I hope you found today's webinar as valuable as I did, and if you did, you can support this work by subscribing to our YouTube channel or signing up for our monthly e-newsletter. And I will be uploading the recording of today's webinar to our YouTube channel in the next few days. And I will send out an email with the link for that as well for everyone who attended today. And yeah, that's everything. Thank you so much, Ryan. And thank you for being here.
Thank you. And I invite anyone who's out there, I don't know who's all in this thing, come on out to Pepperwood. I love taking people out on preserve, and what's better than a webinar is seeing it and getting your hands on it. So I always go, you're all welcome. Come on out. We might put you to work. Anyways, thank you for attending. And I've, honestly just scratched the surface here. There's so much more to learn and talk about even on my end. So thank you all for attending.